Well, welcome to the helium-neon laser experiment. In this experiment, what we're going to do is measure the output of the helium-neon laser at both ends, both from the OC and from the HR, and also measure the XA and the XG parameters, that being the two lengths. From this, you should be able to calculate a whole bunch of parameters about this laser. For example, the GTH factor, and ultimately you could actually calculate the output power of this laser. It's really not all that difficult, and it's something we'll do a little bit later in the program. So what you see here set up basically is a helium-neon laser tube. You've got your anode at one end, that's the high voltage end, and I'll be careful not to get too close to it. And that's the cathode end over there. The power supply itself is this little block behind it. Takes in 12 volts, gives you about 1500 volts out to run, and about 10,000 volts to actually start the laser going. Alright, what you see here is the HR end of the actual laser itself. We know it's the HR because there's a very, very weak output. In theory, we think of an HR as being 100% reflecting. That's just not possible. No one can build a 100% reflecting mirror. This one is only 99.99 something percent. So it's still very, very reflective. But that 0.001% that makes it out ends up forming that little tiny beam. And we're going to measure that. Now, the other side is the OC, and you can see the output is very, very bright from that one. It's probably pushing about 0.5 milliwatt or so. On this particular tube, the OC is mounted on the anode, but there's no particular need to do that. The OC can actually be mounted on either side, anode or cathode. It really doesn't matter. Okay, I'm going to do shaky cam for a second just to show you the actual innards of the tube itself. Now we talked about the cathode and the anode, the positive and the negative terminals on this thing. That little tiny skinny tube in the center between them is where amplification actually occurs. So I'm going to zoom in on this, and you can see the tube in the center. The discharge starts over here at the anode. It goes down that skinny little tube in the center, and it goes inside the cathode somewhere. Now, the actual length of that glass tube is not the entire length of the laser itself. And if I zoom in somewhere on the end over there, there it is. You can kind of see it right there. There's an end of a piece of glass in there. That's the end of that tube, the glass tube itself. You see the end right there? It's just about 1/3 of the way off from the right-hand side of your picture. And that, basically speaking, is the end of that little tube. So that little tube in the center is approximately 2/3 of the length of this particular tube. It varies by tube to tube, and that's where gain actually occurs. Now, what about attenuation? Well, attenuation pretty well occurs within the whole tube. It's caused by things like dispersal, things like photons bouncing off gas molecules, things like that, impurities in the tube. A whole bunch of reasons for it. It occurs pretty well between the two surfaces of the mirror. Okay? Somewhere over here, all the way to this end over here. So XA is from here to here. XG, gain, is right about there to about somewhere in here where that little skinny tube ends. Now, when measuring the power of a laser, it's very simple, of course. We use a power meter. Make sure the wavelength of the power meter is set correctly first. So what I'm going to do is I'm going to zoom in on this power meter for you. Alright, there it is right there. And I go to lambda, and it's set for 632 nanometers. Okay, it should actually be, I guess, 633. 632.8 rounds up to 633. And we'll hit save lambda. Alright, and there you go. And of course, right now it's reading microwatts, 3.2 microwatts. That's very, very little. It's the ambient light in this room right now. Now, we have to zero this meter before we use it. Of course, we always zero it. But there's another catch to measuring a laser, the power from a laser rather, and it comes in the form of this. I'm going to zoom in a little bit right here into the output. Alright, and I'm going to show you the output from this laser on a little white card as soon as I find it here. So let me just put this little white card in here. There we go, right there. Alright, if you zoom in very carefully, you'll notice around this thing there's actually a blue glow. It's very kind of difficult to see on the camera, I suppose, but there's that little red dot right there. Okay, that's the actual output, and around it there's a blue glow. That blue glow is spontaneous emission from the tube just blasting out through the optics. You see, the optics of this tube, oddly enough, are transmissive at one wavelength, yet they're completely reflective at a different wavelength. Now the problem is it transmits blue very, very well. And inside the discharge of that tube, there's neon gas and helium gas. And they have blue and green and a whole bunch of other lines. So if I was just to measure it right now like this, and I would say, okay, my meter is now measuring, here we go, I'll just make sure it's kind of dead center of the meter. All right, it looks like I'm measuring approximately, well here, I'll zoom out and show you what I'm measuring. There we go. It looks like I'm measuring about 546 microwatts. Problem, I have to zero the meter before I do that. All right, so to zero the meter, I want to get rid of all the external lighting, right? Everything that's going to kind of bugger up my measurements. So first thing I'm going to do is turn the lights off in the room. There we go. And that will certainly improve things. And you notice it went down to 540 microwatts. So obviously I was measuring a few microwatts of actual, just light output. Now, the other thing I'm going to want to do is get rid of that blue glow problem. In order to get rid of that blue glow, best thing I could probably do is move this meter off to the side here. Why? Well, the laser beam itself is going to disperse. So if you think about this laser beam, it stays very, very narrow. But the blue glow is going to fan out very, very quickly. So what's going to end up happening is you're going to get a lot less of that kind of spontaneous emission over here than right there than you would get over here. And actually, if I look at the actual card itself with my eye, I can see that blue aura around that red dot. And I certainly can't see it over here, although you know it's there. I mean, there's no kidding anybody, it's there. So what I'm going to do now is finally zero the meter. Easiest way to zero that meter is to use something that completely blocks out light. And what I'm going to do is I'm going to use a piece of metal here. Nothing blocks it like metal. So there it is right there. Now I'm blocking the laser beam itself, that little red beam, but I'm not blocking a lot of that blue light. I zero the meter. All right, and the meter says 0 on it right now, and you wait for a few seconds till it's done. Now, the meter is now reading nanowatts. It's reading about 19 nano. That's very, very low. I simply uncover it now, and I read the actual meter itself. And this particular tube is reading 525.3. Remember, it's up around 546? Well, take a look at the error that I've just eliminated by zeroing my meter properly and by eliminating a lot of that blue problem by moving it away from the actual source of measurement. All right? So I've killed two birds with one stone here. That's a pretty accurate measurement. Let's go do the other end now. So I'm going to move the camera over here. There we go. And I'm going to move my power meter. There we go. Once again, there we go. I will make sure that little red dot goes right into the power meter. There we go. And it looks like it's a pretty small number. Now the problem is, you'll notice that there's a fair bit of light hitting it from the windows in this laboratory. Okay? So it says 10 microwatts. I don't know if I really believe that or not. Once again, zero the meter. All right? We've taken care of the blue glow problem. You can see there's a, if I kind of shield this in, you can see there's a blue glow around it. All right? So what I'm going to do is I'm going to zero this meter here. And I'll hit the 0 button. Give it a few seconds to zero off. All right, once again it's reading nanowatts, and now we'll read the output. 6.4 microwatts. Again, it was reading 10 microwatts when I didn't zero it properly. A lot of that was probably the windows over there, which are flooding sunlight in right now. All right, so in order to make accurate measurements like this, two things. As far as a laser beam goes, you make sure you move the power meter far enough away from the source that any amount of light that isn't the laser beam itself will simply disperse. So you think about the laser beam stays as this little tiny dot, but the actual blue glow, spontaneous emission, garbage that I just don't want to measure, nicely fans out. Okay? So it ends up being a lot lower over here. And finally, you remember to zero your meter. Oh, a trap that you can fall into, by the way, is to do this. And I've seen people do this before. I'm going to zero my meter here. Yeah. See what I'm doing? Yeah, I'm zeroing the meter all right, but I'm also blocking out all the extraneous light from the room when I'm doing it. And now when I uncover this, what I'm actually measuring is not only the laser itself, but I'm also measuring that window once again. Then the reading is 14.4. We know it's about 6 microwatts, so we're only off by a factor of 250%. Absolute garbage. So when you're going to read something like this, you make sure when you zero the meter, the actual meter sensor itself receives ambient light from around the room itself, and that includes any lights that are turned on, the window in the room, glow that's coming off instrumentation, anything like that, the glow of the laser tube itself, sure. You make sure it's actually receiving that when you push zero on here, but make sure the beam itself is the only thing that's blocked if you can help it. The more careful you are about the measurements, the better these measurements get. Now I do want to point out something about the tube that I just used. Take a look at this thing. All right, you probably noticed there was an output of 500 microwatts. This tube was rated at 1 milliwatt when it first started its life. When was that? Well, to give you an idea at the bottom, it says it was made in West Germany. Not Germany, but West Germany. They still hadn't unified yet. And notice when the warranty expired. It expired in, looks like June of 91. That's 1991 June. That's the warranty expiry date. In other words, it's a very, very old tube that you're looking at. It's amazing the thing even works at all. So don't be too hard on it that it only gives you 500 microwatts of output power, and it's supposed to give you about a milliwatt. This is a very, very old tube that's well beyond its best before date. Alright, this is a much more modern tube. This is a Mel's Griot tube. I say modern, it was probably built about 15 years ago or so. But it is a little more modern design than the one that we just showed you. The output of it is almost 2 milliwatts coming out of the OC, despite the fact it's actually about the same size, if not a little bit shorter than the other tube. So you look at this tube and you say, so why does it output so much more power than the other one? It's not as if the physics of the tube changes. The actual gain of the actual HeNe medium is about the same. And if we take a look at this tube, I'm just going to move the camera a little bit closer. And if we take a zoom in on this itself, you'll notice it looks about the same as the other tube. There's an anode over here, and there's this long skinny glass tube that goes down the center, and there's a cathode at the other end, so really it hardly has a difference. The big difference in this tube is the actual length of the gain medium itself. Now you'll remember the other one was maybe 2/3 of the way through the tube or so. Well, this particular gain medium starts at about here, and it goes all the way almost to the cathode at this other end. In other words, XG from there to there is almost as long as XA, which goes from there to there. They simply built the tube with a longer gain medium. Now, flip side to this, you look at it very quickly and you think to yourself, yeah, but I mean, you only made the gain medium from, on the old tube it was this long, you only went to this long, so you barely made it any longer. It doesn't explain having 4 times the output power. Yes and no. Think about gain. Gain is an exponential quantity. When you double the actual length of the gain medium, you don't get double the output power, you get a lot more than that. Okay, so basically speaking, something like gain is going to be an awful lot higher on a laser like this. You have a lot more gain medium between here, and so you're going to get a lot more output power. Obviously, a newer laser will have features like this. In a lot of cases, they tend to make the actual gain medium darn near the length of the actual thing itself, and this way you get a heck of a lot more output power from the laser. Alright, so in conclusion, you can see 3 different tubes here made by 3 different manufacturers. They all have a lot of things in common. Each one has an anode, which is the positive terminal, the high voltage terminal, and each one has a cathode on it. The cathode on a helium-neon tube is always a large cylinder like this. The anode's a very small thing. Through the center on all of these tubes, you can see that skinny glass tube in the center, and that's where gain actually occurs. Obviously on a higher powered tube like this, you've got a longer gain medium, And on tubes like this that put out lower power, each of these rated for about 1 milliwatt each, the actual gain medium is an awful lot shorter on these things. So basically they all have a slightly different characteristics, but they all do the same thing. They put out different power ratings and such. If you look in the actual Mels-Griot tables of the tubes that are available, that's this manufacturer here, you'll see that the tubes go all the way up to almost 1 meter in length. So you can get very, very large helium-neon tubes that put out very, very large powers correspondingly. Most of the ones that you're ever going to encounter in terms of being able to use them in a lab and things like that are going to be similar to these. They're going to be around 1 milliwatt or 2 milliwatts and approximately the same length as these tubes.